Hello guys, welcome. In today's video, I'm going to show you how to program an STM32 only using registers. So right here, I'm going to select my STM32 F411 and create a project for that. So let's call that Bare Metal demonstration. And here I'm going to choose an empty project so that I don't have all the HAL libraries auto-generated. So if we get here in the source file of our project, you'll see that we have pretty much nothing. So this is just a warning. We don't need this. I'm going to remove that. So we have our main and our forever loop here. Here I have all these header files that contains the definition of the different registers I will need for my STM microcontroller. So I'm just going to copy them and paste them in my workspace. So here's our project, includes, and I paste everything here. And I'm gonna add this header file in the project. And let's compile this. Okay, no errors, no warning. So we are really able to start code with that without any problem. First thing first, I'm going to configure the clock. But to do that, I will use the first project as a reference. So right here, we're going to go and take a look at the clock tree of the project in the HAL version. As you can see here, we have a clock tree, and we're going to use these values of the PLLM and P and the different values of the prescaler. You can calculate them, but I think it's just easier and safer to use what's already configured by this system. So I already have the values here, so I'm just going to copy that. And let's go back in our project. So here are different values for the PLL. And to configure our clock, let's get some inspiration from the configuration made by the HAL library. And to do everything that is register related, you need to use the reference manual, not the datasheet. The datasheet is okay, but it's not as detailed as the reference manual. With the reference manual, you can find all the registers you need to program your microcontroller. So let's take a look at this. This is how they configure the clock here. So it's HAL RCC power clock enable. So we go in our manual and we're just going to type, look for power or maybe RCC. You see that we have a lot of occurrences, so we can directly go here in the RCC and look at all the different registers that we have. And if we place ourselves here, we're gonna look something which is power related, or instead of doing that, we can look at power clock, for example, and see if we can easily find that instead of RCC. So I'll do power clock. We don't have that, so I'll just do power. I have less occurrences. So, oh, I found something. So here I have the power interface during sleep mode. That's not what we're looking for. So yeah, here we have power enable. And if we look at the description, what does that say? Power enable. power interface clock enable. So that is what we are looking for. And it is here in the RCC APB1 and R register. And it's bit 28. So we have to set bit 28 of this register. So how it's going to look like is we just do RCC pointer to APB1ENR, APB1ENR, and then we are going to set bit number 28. So one unsigned, and here we're going to right shift that, or my bad, left shift that from 28 bits. And this is the definition of this is how we enable the power clock. And then we're going to do the voltage scaling configuration in the power regulator register. We're going to do the same exercise, and if we can quickly find what we want, so we go into power register and look at the registers. We only have two, and here, as we can see, we have this VOS, which is the regulator voltage scaling output selection. And if we go slightly lower, you can see scale mode 1 corresponds to 1 1. So if we set the 2 bits of the VOS here in the power control register, we will configure the voltage scaling as it is made with HAL. Okay, since I'm not gonna do that for the entire video because it's gonna be very long and boring, and I already have that here, I'm just gonna copy and paste that directly here. So this is pretty much the entire clock configuration. So the point of this video is not really to do it line by line, and it's just to show you that whatever you have, you can find it inside the manual, and you don't even need to know the precise location. You just have to look at what you want. Can be RCCs, everything that's clock related, everything DMA related. You look at the registers, the timer, and you can find everything you want in the manual. Just do the right research, and of course you can also inspire yourself by looking at programs on the internet and all those things. And but one thing that I also wanted to add regarding this, you will see that let's just go here for the PLL configuration quickly. RCC PLL configuration here, for example, here, you will see that they will have this kind of comments here that will say these bits should be written only if PLL is disabled, for example. And so it means that there is a certain order in which you have to do things. For some things, the order does not matter, but for other things, for example, here, the PLL is turned on after the configuration of the different coefficients M, N, P, etc. Because the PLL is actually made up of these things, so it only makes sense that you finish the configuration before and then after you enable or you turn on whatever device you want. It's true for the clock, it's true for DMA, I2C, etc. There's always I would say the configuration comes first, and once you finish, you enable whatever you want to work with. And these are really the kind of things where you have to pay attention. And also, if we go back here in the HAL configuration, there are things that are, I would say, a little subtle. For example, like the flash latency. It's important, but it's just in this tiny little if condition that you're going to see that, and it's very easy to miss that. So sometimes it's also a good idea to just go on the .ioc and have a better look at how a specific register is configured. If we stay with the RCC, you can see that there are things that do not appear in the main.c, but that you have here: instruction cache, prefetch buffer, data cache. Those are all bits that you will find in the power register that you have to enable if you want to have something that is working correctly. So this is for the clock configuration. Next, we're going to do a custom delay function that works exactly like the HAL delay using the same Systick timer. So let's do that. The reference manual has a lot of information, but when it comes to the Systick timer, you won't find that much. Here they're just telling you that when you want to use the Systick timer, you can use it with a prescaler of 8 or without a prescaler. You don't have any additional information regarding how the Systick timer registers look like, these kind of things. But at least in this is the nested vector interrupt table where they define the different priorities of all the interrupts that you find in the board, on the microcontroller. And as you can see, I mean, there is something here with the priority. The higher the number, the lower the priority, or the lower this number, the higher the priority. It's a little counterintuitive. And you can see that Systick has a low number, which means that it has quite a high priority. So Systick is really on top of all these other interrupts. So if you're in a situation where you have nested interrupts, which means that you have uh, multiple interrupts happening at the same time, if Systick is also running, the thing is all the other interrupts will pause and Systick will be the only one doing its thing, which may or may not be a good thing. It really depends on the importance you give to, it depends on what you're doing, you know, the importance you give to your interrupt. And hopefully we have a lot of them which are settable, and it means that you can change, you can lower, or should I say increase the number of the priority to make the priority actually lower so that all the interrupts that you find more important can happen without them being blocked because you have, for example, the Systick that is running at the same time. So here I have a document from Dr. Yifeng Zhu talking about Systick, and he also has a YouTube channel which is Embedded Systems and Deep Learning. I highly encourage you to watch his channel. It's very interesting. And he also has a video that talks about the Systick. So you can see that the Systick is a down counting timer, and here are all the different registers of the Systick timer, where you have the Systick control, low, this is pretty much the auto reload register. This is the value of the counter, this is the calibration. So but Systick is pretty much just a basic timer with a very high priority. So as you can see here, he disables the Systick and then he gives it a number of ticks. And this is essentially the value of the auto reload register that allows you to define at what frequency your Systick is going to be, the Systick interrupt is going to be called. And here is what I was talking about earlier, setting the priority. So right here he is increasing the number to the maximum, which means that he's lowering the priority of Systick. After he finishes all the configuration, at the very end, he enables the Systick. And here is how he implements his own delay function. And I mean, I pretty much did the exact same thing here. So we're just going to copy and paste that. This pretty much means that I am just dividing the original 8 megahertz that I have for my clock by 8,000, which gives me 1 kilohertz, which gives me a tick of 1 millisecond. So every millisecond, my interrupt is going to be called. And by combining this with this delay function, I can implement a precise delay that's equivalent to the HAL delay that we usually use when we're using the HAL library. And the last thing I wanted to talk about is the PWM. So here I also have a function that I already wrote. Just going to copy and paste that. If we go here in PWM mode, here you have the description of everything you need to know about PWM regarding this timer. They give you the entire procedure to configure the PWM. So you just have to go and look at these different registers in the document. Now, what I want to talk about is, let's start with the polarity and the relationship that it has with the PWM mode. You see, you can have PWM mode 1 and PWM mode 2. Basically, if we look at things from an electronic standpoint, the PWM mode 1 is going to be a non-inverting comparator, and the PWM mode 2 is going to be an inverting comparator. But not necessarily, because the PWM mode is entangled to the polarity. The PWM mode just tells you which what is active and what is not active. And active does not necessarily mean it's high level, and inactive doesn't mean it's low. So depending on how you're going to configure the polarity, PWM mode 1 can become PWM mode 2. By default, if we get a look, I mean, I think it is, what register is it again? I have it somewhere here. So it's in the CCER register. So let's have a look at that register. And you will see that here, capture compare OC1 active high. So if the bit is not set, if it's in reset position, its default position, the active state will be logic level high. And if you set that, then the logic level is going to be low. And here in my example, it is reset. I mean, I could have just comment it, because by default, it's already in reset. So it means that it's polarity high by default, even if I don't do anything. Another important thing that I want to talk about is preloading. What does preloading mean? It pretty much means that the value of the register is not going to be changed immediately. It's going to be stored in what they call a shadow register. And after an event happens, then it's going to be pushed into the active register. So practically, what does that mean is, let's say that you have an auto reload register of 5,000, for example. And then at some point in your code, you change that to 10,000, for example. And what will happen is if your counter is, let's say, at 4,900 and something, and it will keep incrementing, and even though you have changed the value to 10,000, it will overflow at the previous value, which was 5,000. And after that, when it will start counting again starting from 0, then it will count. It will now overflow every time at 10,000 like you wanted when you change the value. So the thing is, the change is not going to be immediate. I mean, the counter was still incrementing in that old, I would say, configuration, and it didn't finish what it was doing. And if you change that brutally like that, you may have some kind of unexpected behavior. So the interest with preloading is it protects things a little bit. So what was going on will finish, and after that, after the event, which can be an overflow, an underflow, or something like that happens, then from there the update is going to take place. And if you don't, of course, have uh, the preloading enabled, the change is going to be immediate with whatever consequences that come with that. So, and if you've watched my video, you'll see that most of the time I have this disabled .ioc file. If you go, you really have the option of having the auto reload preload. I usually leave it as disabled because I don't change the frequency. I don't change the auto reload register value during runtime. I'm always at 50 hertz or something like that. So I don't need that. But if you are in a situation where you have to change the value of your auto reload register, you should enable preloading. And preloading does not concern only the auto reload register. When you're doing PWM, it is fundamental. We can go back. We can go back here in the documentation and see what they say about that. They say it's somewhere here. The corresponding preload register must be enabled by setting the OCXPE bit in this register, and eventually the auto reload preload register blah 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 for the ARPE. This is for the auto reload register, and this is for the CCR, the capture compare register. And you can see here they say it must be, and for the auto reload register they say it can eventually be preloaded. Because when you're doing PWM, you definitely change your CCR, you definitely change the duty cycle, and you may or may not touch the auto reload register, aka the frequency. And if we look at what they're talking about here in the CCMR register with the OCXPE bit, I mean, let's go there and take a look. So for timer 1, it's going to be CCMR1 and OC1PE. Okay, this is for the channel 2 of timer 1, so we can also do that with this. So you can see here, output compared to preload enable. When you're doing PWM, you have to use it in the preload mode. But this is the output. The thing is, it's a little ambiguous here because you technically cannot really preload the output, because the output is, I mean, it's the output. It's either high or low. It's not like the auto reload register that is a value that can be stored in some shadow register. Now the thing is, even though they say it this way, on a practical level, it means that you have to preload the capture compare register. So if we go into the CCR, let's take CCR1, you'll see what they say. CCR is the value to be loaded in the actual capture compare register 1 preload value. So it is loaded permanently, blah blah blah, all these, and they talk about the bit OC. Here it's OC1, it's OCXPE. So there is a direct relationship between the CCR and the OCXPE bit being in the preload mode. So essentially, when you're doing that, it actually means that you're preloading the CCR. And for the reasons that I explained that come with the kind of instability that you may have when you don't have the preloading enabled, you uh, you just cannot uh, implement a PWM without the CCR uh, preloaded, because the value is constantly going to change. And finally, regarding the PWM, you have this MOE bit, which is specific to timer one. Other registers, other timers don't even have this register. And if we go back again here in the PWM mode, where they're talking about things, they talk about the MOE, OSE, SSI, and all these here with the BDTR register. The thing is, it's very easy to overlook this and just focus on this one. As long as you don't enable this bit, your output will remain disabled. So you have to, and these are the things that you are completely unaware of when you are using how to uh, configure your PWM signals. So since I don't want the video to be too complicated and too long for this little demonstration, I'll just stop here. And anyway, you have the entire code, not this one. This is just a simple demonstration, but you have the entire code of the Exos arm in the bare metal version, and you also have the code, of course, in the HAL version. Everything is in the same GitHub repository that you have. Uh, you have the link in the description. Since I'm using STM debugging is quite easy. I'll just come here in my debug configuration. I choose the project I want, Baremetal demonstration. I come here, search project, okay. I make sure that I have SD link, then I do debug. And now we can switch. So right now we're gonna debug. And one thing is, when I was implementing I2C, uh, having this, looking at the registers really helped me a lot. So you can always check this. So you can see that my motor is moving accordingly to all the configurations that I made. The delay is okay, so 1 second and 2 seconds. So this is it for today's video, and this video is the last software video regarding this project. So the next video I'm gonna make is gonna be about CAD design and 3D printing. I hope that you've learned one or two things through this entire series of software videos. Okay guys, see you soon, and stay tuned.